choppy, so I apologize in advance if I'm going to have to double check on what you guys are saying. Like it's kind of like one of those ones where the audio is dropping out like only like 10%, and so but I have to extrapolate what you're saying sometimes. So.
Okay. Is that something on our end, Ben?
No idea, of course.
Sorry. Yeah, I was asking our fearless leader.
I think so. We can try restarting the call.
It's going okay at this exact moment. I mean, you guys are the pros, but I mean, I've been on a lot of webcons over my career, or at teleconferences rather, and audio stuff you just never know. I mean, maybe somebody here at Goddard's downloading like a Netflix movie or something, or whatever.
Yeah, the tricky part is video is 80% audio, so I want to make sure we really get the audio like right. And if you're struggling to understand that would be bad too.
Yeah, I mean, it's at this exact moment, it's okay. And even when it was bad, it was I could mostly guess what you were saying.
Okay. The other thing we can do is we can turn off your return video to reduce the amount of bandwidth necessary going back to you. But while it is a live show, we can edit the archive after the fact. So if we hit a point where it's just not viable anymore, we can just kind of stop. Mm-hmm. We'll make a mental note of the last question asked. We'll stop. Sure. We'll fix the technology. We'll re-ask the question and continue from there.
Yeah, no, that's totally fine. It's exactly just like it's a live show. So yeah, totally.
Yeah, cool. All right.
Okay, so just to kind of give you an idea of like what we'll be kind of talking about. So I'll introduce you, and then we're kind of just going to dive right in. We're going to start off basically just discussing some Maven stuff. Yeah, basically just the why and the how behind it.
Right.
And kind of the future of it. And then we'll be sprinkling in questions from our live chat room intermittently. And usually they come up with really great questions. Yeah, so that's kind of a cool element of the show. And then from there, I think we'll transition into talking about Juno. Because I think folks would love to hear about that.
Okay. Yeah, so you guys did your research and you noticed that I actually do work on Juno as well. So I'll be happy to talk about Juno.
Oh, this is an amateur hour. Come on. Just kidding.
Hey, I'm just saying. I did not broadcast the fact that I could also speak about Juno if you wished.
Sounds like it sounds like you're really into magnetometers and magnetism and magnetospheres and all that other terrifying stuff in space.
It was attractive to you.
There's going to be plenty of that throughout the interview. I'm sorry. Dr. Jared Espley. And you're currently at NASA Goddard, correct?
Correct. That's right. Okay. And that's my current professional affiliation. I'm actually also literally at NASA Goddard as well.
Radical. Literally and professionally. Got it. Dr. Jared Espley. Just kidding. And then from there, we'll probably venture into like more things, just like kind of giving it a human aspect. So wanting to know more about you as a person. So like why magnets, or like why Mars, or why D&D?
Right.
I mean, why not D&D?
Yeah, absolutely. I'll be delighted to talk about all that. So
beautiful. Okay, great. Does that sound okay, Lisa?
That sounds great.
Oh, I missed you so much. All right, Dr. Jared Espley. And planetary scientist, is that okay?
Yeah, that's usually the job title that I prefer.
Beautiful. And and you are a dungeon master, right?
I do.
I'm going to sprinkle that in. All right.
Yeah, that's fine.
Dr. Jared Espley, NASA Goddard planetary scientist and D&D dungeon master. Program scientist for Juno. And kayaking. Whoa.
Are you super stalking right now?
I am sorry. I know. I already read this, but then now it's like sinking in.
Yep. Yeah, pretty much D&D and whitewater kayaking are the two
whitewater
major hobbies that I've still managed to keep going, even now that I have a couple little kids to throw into the balance as well. So that I used to claim that I had 3 hobbies, which was computer games, D&D, and whitewater kayaking. And if you guys know parents or parents yourselves, you know that something has to give eventually.
Oh yeah. Was it? What was your?
It was the computer gaming.
What was your PC gaming? Let me guess. Was it? Was it Blizzard related at all?
It was Blizzard related. Yes, I'd spent a lot of time playing StarCraft 2. Actually,
Yes.
not WoW. So my highlight of my computer gaming career is I managed to luck my way into Diamond League on StarCraft 2, like literally like for 1 league, just very temporarily. So.
Radical. Well, your cool points just shot up in my book.
Not sure about that, but yeah.
Oh, you're in a safe place. That is all very much congratulated in this environment.
That is totally why it's cool to talk in a show like this. There's, obviously I tried to do a little bit of my research as well, check you guys out, and it was clear that, the show and the target audience is it's a safe place. My peers, people with whom I feel very comfortable.
That's really funny. I never thought of the guest doing research on us, and now I'm like, like,
always.
I think you guys have done that for us before.
I know, thank you. We're so flattered.
Yeah, I mean, if you get a call from the BBC, you kind of assume that it's on the up and up. And you guys obviously have a great
But we seem shifty.
demographic. I'm not trying to denigrate tomorrow's podcast, but I was like, well, okay, I'm not sure I've heard of these guys. Let me check them out. And you guys look totally legit. So delighted to be with you.
Yeah. All right. So, Juno program scientist, and science team co-investigator on Maven. Does that all sound accurate?
Mm-hmm. Yeah, that's right. You can on Maven, one more. That's fine for an intro. If you ask me the question once we get talking, I realize people are watching already, but I can clarify that not only am I a science team member on Maven, but I'm also the magnetometer instrument lead.
I see that.
So, yeah. So.
Very cool. Beautiful. Yeah. We'll definitely elaborate on all those neat titles for sure.
Yeah. I don't need the titles, but just if people are interested in how science teams are constructed, that's something I'm also always delighted to talk about. People are always curious what it's like to work at NASA and how science teams are and how science teams get put together, et cetera. So, sorry, gotta wave my arm around some hours. Motion detector turns my lights off. You would think that bobbing my head back and forth would keep the lights on, but it doesn't.
Beautiful.
2 minutes.
All right, let's see.
I watched a couple of you guys' previous shows, and it looks like you have a number of hosts. How do you guys rotate through your hosting duties?
Yeah.
Well, we get assigned. We pay Ben some money, and
We sign over the rights of our firstborns, and he gives us airtime.
yeah.
Pretty fair, if you ask me.
Good thing we're millennials and can't afford kids anyway.
Good thing we're not going to have kids until we're like 50, so there's that.
Yeah, I'm somewhere in between millennial and Gen X. It's always I'm never quite clear where I'm at. So
Right? They just keep shifting that line.
They really do.
Some days I am, some days I'm not. Whatever.
Yep.
I just claim it because I'm financially a millennial, so what the heck?
Right.
I identify as
Right?
financially millennial.
Oh my goodness.
I think so.
As will ever
be.
be.
All right. Whew. All right, let's do this.
You got this, Jade. It's like squats.
Those are scary. Hello, friends of tomorrow, and welcome to the show. Today we have the vast pleasure of sitting down with Dr. Jared Espley, a planetary scientist at NASA Goddard who's responsible for working on both Maven and Juno. And here he is sitting here right with us today. So diving right into it, Dr. Jared, sorry, can we redo like all of that? I'm sorry. I didn't give our names. Is there anything else I missed? Oh, I missed saying which orbit it was. Welcome to orbit 12.15. Oh, he's coming out here. I'm sorry. Was it that bad? Was that bad? He has to come out here.
It's hard to yell through the glass. Yeah, so Orbit, quick introduction to yourselves.
I'm Jade. Sarah.
Yep, and then
Sup.
Yep, I need a sup.
Jared Esley.
And then introduce the Dungeon Master.
Yes!
Yeah.
You don't have to remember that, but.
Oh, I do.
And then that's it. Just jump into it. Just remember, we do not want to hear "Thank you for joining us" because it's
I
that
know.
weird, awkward moment.
It is very awkward.
Avoid the awkward moment.
You'd think I'd been doing this for over a year and a half already. Go on.
One more time.
Oh, they gonna bring it in from dark? Oh, sorry. Well, hi there, friends of tomorrow. Welcome to Orbit 12.15. My name's Jade. This is my lovely co-host, Sarah. And today we're sitting down with Dr. Jared Esley of the NASA Goddard, and he is not only responsible for working on Maven, but has also done work on Juno, and is also a D&D Dungeon Master. We will delve into all of those things starting right now. So, Jared, just kind of diving right into it, I really wanted to start off talking about Maven because we think it's a little bit of an underrated Mars mission. So can you just kind of explain what you specifically do for Maven?
Sure. No, I do appreciate the interest in the Mars program, and specifically, like you say, on Maven, which maybe doesn't quite get quite as much attention and glory as some of the rovers that are on the surface. And in part, that's because we're an orbiter, so we're in orbit around Mars, and we've been in orbit for several years now, actually, coming up on 5 years. And our primary science goal is to try and understand what happened to the Martian atmosphere over billions of years and how possibly the Martian atmosphere was blown away bit by the solar wind. And so we can go into that in more details as we continue talking, if you'd like.
Mm-hmm. Always.
Yeah, absolutely. So it's basically studying the Martian atmosphere. So why? Are we doing this because we can foresee this potentially happening to Earth? Or what's kind of the, not only the scientific payback with this, but also, I guess, how do we apply it back down to the science we're doing here on Earth?
Mm-hmm. Yeah, those are two great questions. Both, what's the intrinsic science that we're trying to do at Mars, and what are some of the broader implications of what we can do with that science, what we're learning? So let me try and answer the first part first, which is about the basic context of what we're doing with Mars science. So what we know is that Mars used to be a very warm, wet, possibly habitable. I noticed I didn't say habited, but habitable. There could have been life because it was warm and wet place. And we know that by looking at the geological evidence. We can see on the surface that there are dry riverbeds, dry lakes. We can look at the mineral evidence. We can see the different types of minerals. So some of the results from the Mars rovers tell us about the different clays, about the different types of minerals that get laid down in a water environment on the surface. And so there had to not only have been sprinkles amount of water, but that couldn't be it. It had to actually be copious amounts of water that were on the surface to lay down these riverbeds, dry lakes, and all these minerals. But then obviously we look today, and obviously Mars is a cold, dry, inhospitable environment today. That's just obvious looking with our rovers and our orbital assets. And so that's the context in which Maven comes in, is we have this mystery, this fundamental mystery where we had a warm, wet, possibly habitable environment in the ancient Mars. And today we have this cold, dry environment. And so what Maven is designed to do is to investigate one of the primary hypotheses about how that could have come about, which is that we think that the atmosphere was in fact thicker and warmer, and therefore the surface was much warmer at Mars billions of years ago. And then gradually over time, that atmosphere got eroded away by the interaction with the solar wind, which basically streams off of the sun all continuously. And for billions of years, bit by bit, the Martian atmosphere might have been stripped away. So that's the hypothesis that we've been investigating with Maven.
I love it. And so let's cut to the spoilers. Is that correct? That's the hypothesis you've been working on.
Yeah,
but
right.
Is it real?
So that's exactly. Yes, I laid out the hypothesis. Is that correct? Great. Yes, it does appear to be true. So, okay, all right, we're done here. We can move on and talk about what
No, not at all.
So
We're going to
many
dig deeper.
things that we can, so many complications to that story. But the bottom line is that hypothesis does seem to be borne out by what we're seeing with MAVEN today. And so what I mean by that is, again, this is an orbiting spacecraft. And so we're in this very elliptical orbit. So we come in very close to the planet and then we go relatively far out, several thousand kilometers far out. And what we have on board is we have a variety of science instruments that are designed to capture the particles, the atmospheric particles that are flying away from the planet or not. And also instruments on board to measure the electrical and magnetic fields, which control which direction those particles would go. And so basically with this orbit that we have, and like I said, we've been there already for 5 years, we are effectively trying to create a net to capture all these particles. Obviously, with just one spacecraft in time, we can't actually capture all the particles that are flying away from the planet and start to try and extrapolate what's going on the broader scale. We can't do that with just one spacecraft at one point in time. But gradually over time, over these many years that we're in orbit, that we are able to start building up this net that's helping us to understand how many particles are flying away from the planet at any given time. And now that we've done that, we have, in fact, started to capture that there's, in fact, a comparatively tiny amount of oxygen, a comparatively tiny amount of hydrogen that is flowing away from the planet today. It's about 10 to the 25th particles, which is a huge number, but that's literal individual atomic or molecular molecules, particles. And so when you add that all up, then that actually comes out to like half a gallon of water per second, which is not very much. But you multiply that over billions of years, and it does look like, in fact, that it bears out this hypothesis that I laid out at the beginning, that the Martian atmosphere has been blown away bit by bit. So that's what we think is our current understanding, is that, yes, there definitely could have been a significant amount of loss from the planet. But as soon as you peel back the layer and you start trying to answer even more complicated questions, then you realize there's a lot more going on. There's a lot more confounding factors. And that goes to that question, that other question you asked at the beginning, about how we can apply this information to our understanding of our own planet, our understanding of other planets in the solar system, and our understanding of other planets outside of our own solar system. Let me get my light to turn back on.
Yeah, no worries. It's a friendly hello.
I was trying not to lose my train of thought as I was waving, but apparently every 5 minutes I'll need to move dramatically enough to keep the motion.
And we're okay with that.
Yeah.
Absolutely.
If you feel the need,
and
just dance
we
a
can
jig.
even join in.
Yeah.
Spontaneous breakout
dancing.
dancing.
So we have a running gag in our science team that when somebody doesn't have a something that they're really ready to say, then somebody could just jump up and do like an interpretive dance of the particles from the planet. So there's always a joke about, well, hey, Dave, why don't you get up and do your interpretive dance again? So I won't actually do the particle flying away interpretive dance for you guys right now, but I will occasionally.
Why not?
Keep the motion here, yeah.
Please do. We love interpretive dance.
Thank you, but
it's kind of the cornerstone.
Yeah, we'll join in. You can teach us the particle escaping interpretive dance, and every time the lights go out, it'll be a dance break.
Beautiful.
Right.
So bringing it to the chat room, there's actually a few folks asking some really interesting questions about Mars's magnetosphere, from James Johnson, Gregorius Sadarmo, and a couple of others. I'll kind of combine the questions into one. But they're essentially asking, is there any theory on how Mars lost its magnetic field, or if it even had a magnetic field protecting it in the past? Yes.
Okay, great. Let me try and answer that question. Let me step back and give some context for everybody else. I won't directly answer the question immediately. I'll give the context. So in general, many planets throughout our solar system, and we presume throughout the universe, have planetary-sized magnetic fields. And so that includes your own planet, Earth. And what we think is happening there is that if you start with any sort of tiny little seed magnetic field, and it doesn't really matter what the seed magnetic field is. It could be something from solar wind flowing out way in space, carries a magnetic field with it. A tiny little seed magnetic field, if it flows past something that's electrically conducting, in other words, for example, iron, molten iron in the core of a planet, then it can produce induce a magnetic field there, and that can enter into a feedback cycle, and we call that a dynamo. And those dynamos create a planetary-sized magnetic field to get this feedback loop of motion and electrically conducting material combined together. So we think that's what's happening at Earth. We've had this strong planetary dynamo, planetary magnetic field. We know that's happening at Jupiter and at Saturn, at Uranus and Neptune. It's happening at Mercury. But it doesn't seem to be happening today at Mars. When we fly by with previous spacecraft and MAVEN, with our magnetometer, an instrument that can measure the magnetic field, we don't see any strong planetary-sized magnetic field. Instead, what we do see at Mars is we see some patches of the crust that still seem to be strongly magnetized, but they're very localized. And so we think that is not originating from the interior of the planet. It's not a planetary magnetic field, but there's parts of the crust that are magnetized. And so what that does is that gives us a clue about what might have happened at Mars. And so the interpretation is that basically the Mars as a planet would have had a planetary magnetic field originally. And then at some point, that planetary magnetic field ceased. And the most likely scenario is that Mars is just smaller and therefore literally had less heat in it. And so very simply, once the Martian core froze and was no longer molten iron like ours is, then there was no longer the motion, there wasn't the motion. It was still electric and conducting, but it wasn't moving around. It sort of couldn't create this feedback loop that the dynamo needs. And so at that point, the dynamo would have ceased at Mars, and the magnetic field that was there disappeared. And what was ever going on at that time, if there were rocks that could be magnetically susceptible, have some iron grains in them or whatever, hematite grains in them, then they would have kept the magnetic field that they had at that time. We see that on Earth. Like individual rocks can pick up the magnetic field that's near them. But on average on Earth, it all cancels out, especially in the background of the planetary magnetic field. But at Mars, these individual rocks would have just kept their magnetic field. And then if nothing happened for the next billion years, that's what the magnetic field we would still see. So that's the interpretation, is that Mars had a magnetic field, global planetary magnetic field, and then gradually over time that went away, presumably because of the lack of sufficient heat. And then the crustal fields kept their configuration unless something happened to them, like an impact crater or volcanism. And so that's why on the surface, wherever we see large volcanoes or large impacts, the magnetic field signature has disappeared.
All right. So we do have a question from our chat that's following up on the magnetic fields. So you've got a magnetometer on MAVEN, and you're project lead for the magnetometer there, yes? Yes.
That's correct, yeah.
All right. So how do you use the magnetometer system? And Rebel on our chat room is asking, how do you use the magnetometer system, and how can you make a map from that data?
Yeah, it's a good question. Okay, so first of all, let me say magnetic fields are really mysterious, is what I would study for a living in some sense. On the other, as a fundamental thing, they are, one of these fundamental forces of nature, and so what we do with them in space is perhaps slightly more straightforward. There's two major categories of magnetic fields that you can measure in space. One's the ones that I've been describing already, where a magnetic field is locked into or part of some physical part of the planet, either the core or the rocks or the crust or whatever. So that's one category of measurements that you can make with a magnetometer in space. You fly close to a planet, you measure how the magnetic field looks as you fly close, and especially with an orbit, it's great because you can kind of see how it kind of changes as you go flying by. I'm going to try and do like a little diagram with my hands. So you've got the pointing of the magnetic field in one direction as your spacecraft flies by. You can imagine how basically the compass needle would change as you're flying by effectively. And then the other category of magnetic fields that you can measure in space are magnetic fields that are produced by very energetic gas, what we call plasma. So the upper atmospheres of planets and the solar wind itself and space, interplanetary space, and even interstellar space is filled with plasma. And that just means particles that have gotten enough energy that they've become ionized. And once they're ionized, then electromagnetic fields can be produced and or control the motion of those particles. And so we can measure the magnetic fields of the plasmas, of the ionospheres, of the magnetospheres of the upper parts of planets. And so that's another aspect of magnetic field measurements that we make. So let's see here. That was part of the person's question, Rebel's question. They asked, how do we use the magnetometer? And then what was the second half of Rebel's question?
How do you build maps from that data?
Oh, yeah, great. So I kind of already addressed that, but it's basically as one orbit pass by itself is not going to build you a map. Mm-hmm. But once you get dozens, hundreds, thousands of orbit passes, then you can gradually be building up a map of where those crystal fields are, because as you fly by every time, there's going to be a slightly different angle of the magnetic field as you fly by. And so over time, you can build those maps up.
Awesome. So I have another question from the chat room, CFIT. The question is actually going back to the little localized magnetic fields on surface rock. So if those magnetic fields are local, are any of those local fields strong enough to affect habitability? So I know we've discovered some magnetic fields on the surface of the moon that cause little pockets of protection from the sun. Yeah. Are any of these Martian pockets strong enough?
Yeah, absolutely. That's a great question. They undoubtedly change the trajectory of particles in the atmosphere. So energetic particles, as they come in, will affect the amount of radiation that the surface receives. I mean, there's several questions of habitability. So the most direct way is radiation. So that's the part that I'm answering. And so, yes, the magnetic fields are certainly strong enough localized to affect the trajectories of the energetic particles, of which there are two categories. So it's just solar energetic particles, which come from the sun, hence the name. And then there's also the galactic cosmic rays. Rays is kind of a misnomer there. They're also really energetic particles. So we could go into the whole light is both a wave and a particle. But anyway, galactic cosmic rays and solar energetic particles, they come in and they're the radiation in space that you have to worry about. The local crustal magnetic fields at Mars aren't going to do diddly for the galactic cosmic rays. They just come in with so much energy. They're produced by astrophysical phenomenon, supernova. Here we go.
Dance time. Woo!
And they come in from the supernovas and the galactic events and extragalactic events. Those things have so much energy, they just go streaming in. They don't care about any sort of magnetic fields. They don't care about our own planet's magnetic field, really. The only thing that really seems to affect their input into the solar system is the sun's magnetic field. It has a very slight modulation on the amount of galactic cosmic rays. So that's not helped by the crustal magnetic fields. But the solar energetic particles are, in fact, definitely potentially affected by the magnetic fields. And they are definitely affected in the atmosphere. The question that some of us are very actively interested in looking at is whether or not the surface, where you would potentially have rovers or astronauts someday, would literally be slightly protected in one spot versus another because of the crustal magnetic fields. And so the answer is we don't really know yet.
And that's okay. That's actually almost more exciting as an answer than having a definitive one.
Right? If it's a yes, why aren't we there yet?
Yeah. All right. So thank you so much for basically explaining all the amazing work you're doing for MAVEN. And while staying on the topic of magnetism and all of that exciting stuff in space, let's go ahead and transition into talking about your work on Juno. Because speaking of magnetospheres, I've never heard of something more terrifying in our own solar system's backyard than that of Jupiter's magnetosphere. So can you delve into a little bit of the work that you did on Juno?
Yeah, I can. So, the work that I personally did on Juno fell into two categories. So earlier in my career, and let me step back. It takes a long time to get to planets sometimes, and particularly it takes a long time to get to planets in the outer solar system. So a typical Mars trajectory takes about 8 to 10 months. Obviously, that could be different if you had some sort of Uber rocket, but most trajectories to Mars take about 8 to 10 months. Most missions to the outer solar system, meaning places like Jupiter and Saturn and Uranus and Neptune and Pluto and beyond, so like New Horizons, take years, many years. So I started working on the Juno project way back in somewhere around 2008, something like that. And at that point, we were developing the instrument, and I was a relatively junior member of the team. And so I was helping to calibrate the instrument, the magnetometer instrument. So that was one aspect of the work that I've done on Juno. And then many years later, it launched, and then many years later, it actually got to Jupiter. So it got to Jupiter in 2016. At that point, I was pretty fully engaged with what I was doing on Maven, but they also needed some help down at NASA headquarters to do something that's called being the program scientist. And I always struggle to explain exactly what a program scientist does. It doesn't mean that they're in charge of the mission. There's a principal investigator, typically, who's in charge of the mission. And that's a scientist at some other institution, or it could be at NASA. It doesn't really matter. The principal investigator is in charge of the mission. And then NASA as an agency is obviously directing the principal investigator and all of his or her co-investigators to implement the mission. And somebody at headquarters, NASA headquarters, has to be that interface to make sure that the principal investigator of the mission is doing what they said scientifically, and also somebody has to be in charge of making sure that they're spending the money they're supposed to. So there's somebody who's called the program executive, who's in charge of the money and the engineering side, and there's somebody who's the program scientist. And that was me for several years. In fact, until just a couple of weeks ago, when I was able to pass the torch on to somebody else. And so as program scientist, my job was to make sure that the mission was doing scientifically what it claimed to do, what it had promised to NASA headquarters it was going to do. So verify that the science measurements that were laid out and agreed upon are being met. And also to make sure that any sort of communications from the project and any interesting science results are being interpreted for my colleagues at NASA headquarters, because not all of them are necessarily specialists in all the different aspects. Mm-hmm. So that's what I did as a program scientist. And then early on, I helped out with the magnetometer. So I got to see kind of from both ends, literally like above the project, again, not in charge, but like from the highest perspective, seeing the whole thing, and then like down in the weeds, like helping calibrate and build the instrument. And so those are things that I've done on Juno.
Nice. And I think that offers such a unique perspective from you personally, because to have, like you said, like that grand vision oversight, as well as like getting into the nitty gritty of the mechanisms behind all this. So, as mentioned before, Jupiter's pretty intense, pretty dramatic, definitely king of the planets, rightly so. So what are a few of kind of the most like profound things you learned during your time on the Juno mission?
Yeah. So we know a moderate amount about what's going on the surface of Jupiter. We actually made a lot of discoveries with Juno about the surface, but that was not Juno's primary purpose. Juno's primary purpose as a mission was to peer underneath the clouds of Jupiter and to try and get a sense of what's going on the inside. Excuse me. And so what I mean by that is that, well, like we've already talked about with Maven, we have a magnetometer on board in Juno. And we have some other instruments as well, like the microwave radiometer and a gravity investigation that allow us to peer into the interior and get a sense of what's going on the inside. And so we're trying to make a sense of how is Juno stacked up on the inside? Does it have a core? How big is the core? What's the core likely to be made out of? What's on top of the core? Is there material that's under super high pressure but is not rocky? Is there some sort of a metallic layer that's on top of the core, and then what's the deep atmosphere look like? So that was the intention, and Juno's doing a great job. Like I described on the Maven, these are kind of slow-moving missions, and what I mean by that is it's not like you just make an immediate discovery just based on one set of observations. You have to build up a map. So what Juno is trying to do is build up a 3D map, and we're about halfway through its mission, even though it's been there since 2016, so going on 3 years now. It's only halfway through its mission, and that's because it has a really large orbit that it's in. It's a 53-day orbit, so every 53 days it comes close enough to the planet to make the observations that are most useful for those interior measurements. So we're only halfway through, but what we know already is that the interior does not seem to have the very finite, very dense core that everybody assumed that a gas giant would have. So most people listening will know that Jupiter, of course, is a gas giant, that most of it is gas. It's not a solid body like the Earth is. But we thought that maybe there was a rocky core on the inside, and it doesn't look like that. It looks like it's got some sort of diffuse core that's spread out, like the mass that's inside there is really kind of spread out. And that, frankly, to me, doesn't really make a lot of sense. That's not really my area of science expertise, but that this is one of the major results that's come out of the mission, is that the core is spread out and diffuse. Another major thing is that the deep atmosphere is connected to the atmosphere that we can see. So everybody is familiar with the Great Red Spot, this huge storm at Jupiter. It turns out that when we flew over the Great Red Spot with the spacecraft, we measured with a microwave radiometer, we could see all the way deep down into the roots of the Great Red Spot. And it looks like they're connected all the way down to basically the layer where the magnetic field would take over the conducting electrical metallic layer. So that great storm is going all the way down, and furthermore seems to have more heat down below than up above. So there's definitely heat driving something underneath the great storm, the Great Red Spot. And then just to take a breath, you might have some more questions, but the third major category of interior science that we've learned from Juno is we learned a lot about the magnetic field. Again, we already talked about dynamos, planetary dynamos. So that all still applies to Jupiter. Jupiter clearly has a planetary dynamo, clearly has electrically conductive material, clearly has it in motion, producing this tremendous magnetosphere, which basically just means where the magnetic field controls things. But when we got really close and we took a measurement of that magnetic field, it looks like it's actually coming from several spots. Mm-hmm. It's coming, as with Earth, from the poles, but there's also spots near the equator. And so it seems like maybe there's multiple dynamos going on. Mm-hmm. So maybe there's conductive material kind of deep down, and then there's conductive material higher up, or maybe we just don't understand. And again, there's a lot of that where we just don't understand. And like I think you said, Sarah, that's a great thing. That's what you want in science. You want to be confused and have a cool mystery to work on. And so that's exactly where we're at with a lot of these things.
Absolutely, yeah. Befuddled is, as I like to call it. Sorry, and I just find this topic so fascinating, just magnetospheres in general. So you mentioned that, it's not just emanating from the poles, but, from the equator as well. So
dance party.
Oh, dance party. Intermittent.
Oh, you got to run for it this time.
You're going to have to do a little better than that, Jared.
The escaping photon.
We know you have better dance moves than that. So when you visualize Earth's magnetosphere, like you said, like north and south poles, and then they kind of jut out like this, like almost like butterfly wings. But because because as you said, Jupiter is gaseous and it's very different dynamics there. Does that have an impact on kind of like, I guess, the chaoticness of its magnetic field? Does it make it a little bit less predictable and a little bit more tumultuous?
That's a great question. I don't think we understand the dynamics of the interior well enough. That's literally what we're trying to understand to really make that connection. Certainly the upper atmosphere is very stormy and is very tumultuous, like you said. And that, like I said, that's another really cool result that we weren't intending to really look for with Juno. Again, the intent of Juno is to look underneath. But we found a lot of thunderstorms and a lot of lightning that's occurring that you can just visually see on the surface that we hadn't really had a good handle of before. So that's a really cool result. Another really cool result from Juno, going to that point of the tumultuousness of the atmosphere, is we never had any good views of the poles of Jupiter before, because most of our observations are from Earth. So you could point telescopes like the Hubble or something, but you obviously can't see above the planet from our own planet. But the way Juno's orbit is, we come in over the poles, and so that's allowed us to see the poles. And there's these really huge circumpolar cyclones, we call them. So they're just circling around the poles. And there's several of them. I always forget how many are on the south and how many are in the north. There's 8 on one pole and 5 on the other pole. And I'm sure one of the viewers can probably look that up and tell us in the chat. I forget. But there are these huge storms, and so why are there 5 of them up there? Why don't they merge together? Because here at Earth, some of the viewers might have heard about the polar vortex here at Earth that's causing all kinds of crazy weather. It's the same idea. You get these storms that create in the poles, but there's only one really here at Earth. And so why are there all these storms up there? So nobody knows. I think it's an open question for the atmospheric dynamicists.
speaking of questions, you've actually answered some of the things from our chat. And Raju Luther on YouTube was wondering what other instruments are on Jupiter and what will they be doing. So thank you for jumping ahead. And we also
there are a few more that I haven't mentioned. There's several other plasma and particle instruments on board that help as well. And probably the instrument I haven't mentioned, but I've implicitly applied, is the JunoCam instrument, which is just a simple camera. In fact, it was not originally intended as a full science instrument. But it clearly, if you're going to go to Jupiter, you want a camera in it. And that's where a lot of the really public-facing results have come out. So people who have been paying attention to Juno have probably seen the images. Well, that's just all from JunoCam. So that's been a spectacular success, I would say. And one more thing about JunoCam before we move off it, everybody should know that data is freely available. And you can go and you can download it and you can manipulate it. So a lot of hopefully some of your viewers are part of that. And that's been a really huge success, I would say. People sometimes make these beautiful pieces of scientific art where it's science data, but it's literally like an art that you hang in your room. And then some people make them like whimsical too. They take the image and they'll make like little cartoony things and make it fun. So that's awesome because everybody can take the data and do what they want with it. And so I think that's really cool.
Yeah. Those images that are coming off of JunoCam, they're one of the things that you might want to look for when you're searching for those images. You want to get the lower saturation images. You want to make sure that you're looking at the original data or at one of those saturation boosted kind of artist enhanced images. Just be sure which one you're looking at. The original data itself is amazing enough, but a lot of the pictures that we see, the really boosted colors with the purples, those
pretty gorgeous.
Those have already been tweaked by people at home. So we want to be careful about that. But the original data is just stunning.
Absolutely.
And which leads me to another question from our chat. CFIT again. Knowing what we know, what instrument change, if any, do you wish would have been included in the Juno mission? Or for future missions, what would you include on a Jupiter mission?
That's a good question. Juno is a very focused mission. Juno is designed to investigate Jupiter, and Juno is designed to investigate not just Jupiter, but the interior of Jupiter. And it had to be that way because it's not what we call a flagship mission. And so it's not a mission like Curiosity, Mars Curiosity or something like that, where it was an agency-driven mission. Instead, it was a focused principal investigator-led mission. So I'm not sure that I know off the top of my head exactly what else I would change about the focus of Juno, but a slightly different flavor of that question would be, what would I want in a Jupiter system mission? And the answer is something similar to what we're doing already as an agency, which is getting ready to send missions to the moons of Jupiter, because Jupiter itself is a fantastic, interesting place, but its moons are really awesome as well. And of course, your viewers will know the four major moons of Jupiter, which are Io, Europa, Ganymede, and Callisto. And so there's a major effort underway at NASA right now to send a mission to Europa, possibly multiple missions, possibly to Europa. And so that would be one thing that I'd be really excited about in the future for a Jupiter system mission, is those European missions. By the way, I've managed to get my autocorrect now to change to not, whenever I start to type European or Europa, it used to fix it to European, but it doesn't do that anymore. So I've trained my autocorrect to respond to my planetary science autocorrect.
Gotta love AI.
Learning computers.
Beautiful. So you kind of touched on to where you'd like to see the future trajectory of not only Jovian missions, but Jovian moon missions. As you said, they're fascinating worlds unto themselves. So then, where would you like to see, I guess, both the Maven and the Juno missions? how would you like to see those continue, and where do you see this ultimately headed? So going back to MAVEN, talking about Mars, so learning all of this information and all of this data about, what happened to its atmosphere, what it was once like in its past, this is very important for looking towards the future. As you know, there's a lot of talk of going to Mars, potentially habitating it. Is that the word? Habitabilizing it? Whatever.
Yeah.
All of the synonyms.
There.
All the
cinnamons.
Anyways, before I keep making a fool of myself, where do you see the futures of these missions going, and what do you think? How does that tie back into, I guess, human exploration of space and getting closer and closer to these bodies?
Yeah, I think we're at a really sincerely interesting time. Like, it's always. Well, we're coming up on the 50th anniversary of the Apollo landings, and so that's really, I think reflective for a lot of us. Not judging, but I'm pretty sure all of us here are speaking. We don't remember the Apollo landings, but I know many of our colleagues do. And I think it's a time to reflect upon how far we've gone, but how much we still have yet available to us. I think it's also exciting how much interest there is in society in general, and also, it's thinking of like SpaceX and Blue Origin and all the other new space tech companies that are out there that are interested in getting to Mars and getting to the moon, with this opportunities for all the upcoming lunar commercial landers and the science opportunities there. There's a ton of opportunities there. So I really honestly think that we're on the cusp of being able to actually push back out into the solar system again, not just with the scientific robots that my career is based on, and my career hopefully will continue to be based upon, but also with astronauts. I think there's a genuine opportunity here that we will, in the near future, all these forces are synergistically working together to push us towards a major next step in exploration of the solar system.
So speaking of that next step, with Mars and what you know of Mars's magnetosphere and the atmosphere, and, well, what you need to have humans live sustainably on the surface, what do you think is the best option for actually having that long-term habitation? What would we need to do?
Yeah, so sometimes people ask, whether or not we would need to restart the planetary magnetic field, because as we talked about, we think Mars used to. This is actually one of the important things that I think is coming out of MAVEN science. It's kind of esoteric at first appearance, but there we go. Then what we're trying to understand is how planetary magnetic fields impact the amount of atmospheric erosion that can occur. Because remember, back to that basic idea that I was describing with what we're learning from MAVEN, is that it seems like the solar wind is in fact coming into the upper Martian atmosphere and gradually blowing away bit by bit the Martian atmosphere. And so kind of the classic story that we've always told is that happens because Mars does not have a planetary magnetic field, and therefore the solar wind particles can directly access the upper Martian atmosphere and interact and blow the particles away. What we're finding with MAVEN is that it's actually way more complex than that. It's really, Mars is a great laboratory for this. And what I mean by that is wherever these strong crustal magnetic fields are, again, not planetary size, but just localized crustal magnetic fields, we can see differences in the amount of atmosphere being blown away. And furthermore, we know from our own planet that actually those solar wind particles do interact with the upper atmosphere of our own planet, and they create the aurora. And that's in large part where the aurora, the southern and northern lights come from. And when that happens, it also seems to be driving away bit by bit some of the terrestrial atmosphere. And we've always had our magnetic field, a global planetary magnetic field. So I think there's a genuine paradigm, I won't call it a paradigm shift, but a paradigm uncertainty, whether or not this classic story that planetary magnetic fields protect a planet, prevent the solar wind from blowing away the atmosphere. I think that's uncertain right now. I think MAVEN's actually shook that up. So, which is a surprising thing, because we kind of expected when we went there that would alter it. So what I'm trying to lead up to answer your question about how we would get to habitability there is, I certainly don't think it's true that we necessarily need a strong planetary magnetic field to send astronauts to Mars. In fact, I know that for sure. We don't need a planetary magnetic field for them to go there. They need to be protected from the radiation that's there. But we're not going to get a planetary magnetic field to do that anytime within hundreds or thousands of years. That technology is beyond us. And we don't need it. We can protect our astronauts from radiation in other ways. So I think our MAVEN science is helping us to understand how planets work better, but I don't think it's directly helps or hurts the chances of putting astronauts there. What we really need are the ability to prospect for resources if we're thinking of like long-term habitation and sizable colonies or sizable settlements. Let's use the word settlements. Because it's one thing to have a few astronauts there and to just go and carry your own resources with you. But like, if you actually want to have lots of people there, you got to make sure you have lots of water available to you. And we just don't know how much water there is. I mean, we know there's ice, but like, where is it? And like, you know, so we would have to definitely start to identify settlement-sized resources if we're going to have a long-term presence there.
Very cool. So kind of wrapping all of this up and getting your why, which is something we really try to do when we're speaking to, you know, folks like you who are just so full of so much information and so much knowledge. So can we get your opinion on why is this all important? I mean, yeah, as you said, like we're maybe not shifting paradigms, but we're not taking them as, you know, absolute truth anymore. And the same thing with like, you know, even with, I know there's going to be a lot of textbooks that are going to have to redraw their diagrams of Jupiter because every diagram I've seen has indicated some sort of rocky iron core. But why, in your opinion, why is this all important? Why did you dedicate your career to these fields? Fields, get it? Like magnetic? Sorry,
Boom.
Go on.
yeah, that's good. I didn't even get the pun at first. I think for me personally, when I started, it was about exploration. So what I mean by is when I was a kid, I wanted to have adventures and go exploring cool places. And clearly the adventures are happening in space, right? Because you can go be a Jedi in space. That's a pretty awesome adventure. And you can go be a Barzumian prince and you know, fight dastardly villains and rescue princesses in space. Okay, that's awesome. That's a great adventure, but that's in space too. So let's go and have adventures in space. So that, I mean, that's definitely where it all started for me, is wanting to have adventures and have exploration. And as I got older, I realized I probably wasn't going to be rescuing a lot of Martian princesses. I wasn't necessarily going to become a Jedi. But I also fortunately found out that when in science, then what you can do is you can explore space, but you also learn how the world works at the same time. And so it's a way of indirectly exploring as well. And so that seemed like a really powerful combination to me. And so that's how I ended up here is I wanted to explore space. Like if I'd had to be if I'd had to become get my schooling in I don't know, English or I mean I obviously I took English, but if I didn't, what I'm trying to say is I didn't decide that I wanted to become a physicist and therefore I will explore space. It was the other way around. It was, I wanted to explore space, and the tool with which we use to explore space is physics and math. So I was like, great, no problem. Physics and math, it's fun, it's interesting. I'll learn that stuff so that I can explore space. And so that's what I wanted to do.
That's amazing. So you basically reverse engineered being a Jedi, essentially.
Well, something like that. I'm not sure. You know, my abilities with the Force were quite the same that I thought they would be when I was 6. But
I think you underestimate yourself, young Padawan.
Maybe he just set himself the right mission as Dungeon Master.
There you go. There it is. All right. Well, Dr. Jared, I'm just going to call you Jared. Jared, thank you so much for spending your Saturday afternoon with us. Certainly, I got a whole lot out of this interview, and it seems like the chat room is just going absolute crazy. Sorry we couldn't get to every single one of your questions, but nonetheless, you were just a treasure trove of fascinating information. And certainly inspiring on top of that. So again, thank you for joining us. Before we say our official goodbyes, of course, this is the portion of the show where we'd like to give a nice little heartfelt welcome, or thank you, to our citizens. These are the folks who make the show possible, like the Escape Velocity citizens here. And what they do is they contribute a certain amount of money per month on patreon.com/TMRO. As we go through these slides, you'll notice the font gets smaller and the names get more plentiful, and that is because there is a tier for everyone. Even my name's up there somewhere. Yes. So thank you again for making the show possible. There it is. I love it. Great wall of names. And again, if you're interested in contributing to the show, yes, you can contribute monetarily on patreon.com/TMRO. Or, as I've said before, you can contribute emotionally or just, you know,
like things.
You could smash that like button.
Yep.
You could subscribe to the channel, share us to all your friends and fam, have us on at the dinner table when you're all sitting and... Anyways, what I'm trying to say is thank you. Continue tuning in. We will see you next Saturday, and we hope you all have a lovely week. Goodbye.
No holds barred. You don't have to participate if you are. If you have other things that you need to do with the rest of your day, absolutely feel free. But this is like this is where we discuss anything and everything you want to. Yeah, Jade's gonna just grill you on DMing and.
Yeah, but that's all right. Yeah, so you're more than welcome to. Hold on. I think we lost audio.
Oh no. Nope. Yep. Oh, call thing.
Sorry.
Yeah.
Sorry, I didn't tell Raph about that.
Oh, just kidding.
Hello.
Yeah, we got you now. I'm sorry.
Okay, cool. Yeah, so I don't know if you heard Sarah, but yeah, so this is the part where we just kind of like shoot the S and hang out. You're more than welcome to stick around, or you're more than welcome to log off. Totally up to you. You won't take it personally.
No, I'm good. Right? I'm good. I had a kindergartner's birthday party that I was with my daughter just before this, so you guys saved me wrapping that up, and I'm going to go join my family for an ultimate frisbee game in a little while. But I'm happy to stick around with you guys for
ultimate frisbee, eh?
Yep.
Surprisingly enough, you're not the first scientist to partake in such a hobby. In fact, just a few weeks ago. Yeah,
my wife's the hardcore one. She plays on one of the women's elite teams around here. But I just go and try and play a little bit and help keep the kids out of trouble. So.
That's awesome. So I know I didn't get to this in the main interview.
Dance party time.
Rude. Just kidding. But, I love how you mentioned that, as a kid, you were always fueled by exploration and adventure. Mm-hmm. And again, I know I didn't bring up D&D during the interview, but everything you were talking about was so interesting. I didn't want to sidetrack us. But you said you also started D&D while you were a kid. So you have this gorgeous campaign you've been, in since you were 8.
It probably changed up a while.
I mean,
I was going to say it wasn't the same campaign. I've been super fortunate to play my entire life, and I do actually have one friend that I've still played with since we were in middle school that I'm still literally playing with these days.
Amazing.
But in general, what's happened is that each phase of my life, I found a new group of friends with whom I could play D&D. So I played with my kids, my friends in elementary school, middle school, high school, kind of the same group of kids, and then. When I got to college, I found a group of friends who were interested in it. And then when I got to grad school, I found a different group of friends who were interested in it. And now as a actual pretend grown-up, here I am in my grown-up life. I found another group of friends with whom to play. And so it's just been continuous groups of friends that I've been able to play.
And the one thing I've always loved about D&D is it's such like a camaraderie building activity. It's like role playing. Yeah, it's all that stuff. But it's like when let's say you get hired and you move to a new city and you don't know anybody, there's nothing more immediately bonding than, wait, you're a D&D player? Like, whoa, what level are you? What are you? What do you play as? So that's so cool. Right. Now, you mentioned you had a couple of little ones. Are they old enough to play yet?
So I have a 5-year-old and a 3-year-old. We do play a little bit together. So my 5-year-old was very invested in the Curse of Strahd campaign that we just finished. I was GMing it, and she took a personal interest in it, which was a little awkward a few times because that's a pretty dark campaign for people who are aware of it. So she would stick around for like the first hour or so, and then we would try and usher her off to bed. And sometimes, my wife was great about it. She would try and get the kids to sleep, but I would also take a break. So we did have to kind of avoid some of the most dark themes. But, it's got a lot of those grim fairy tale type things and I just decided to go ahead and embrace it. So like at certain points, even when my daughter was around, like participating in the campaign, we'd have the witches who are trying to bake the children or whatever, which is kind of a terrible and terrifying idea, but it's part of, our cultural mythology. Yeah. And so I went ahead with it. She doesn't seem too traumatized by it. We have been playing as a family No Thank You Evil, which is a game that's designed specifically for kids. And so she's been super keen for that as well. So what we've been doing recently is before our D&D campaign starts on any given Sunday, is for half an hour before that, we'll play No Thank You Evil with all the D&D, all the grown-up D&D friends, because my daughter loves all the D&D friends as well. We'll play No Thank You Evil with them together, and then she'll go off and go do her thing, and then we'll pick up playing D&D.
So cute.
That's super cool.
Train her right.
Heck yeah.
Yep.
So I'm going to transition back to science really quick because there's a couple of questions still in the chat room, and there's something that I was fascinated about. So a lot of folks were asking about the, the metallic hydrogen existing in Jupiter. So from my going way back to my college days, taking just your basic astronomy courses, we were always taught because there's so much gravitational pressure on Jupiter, the hydrogen starts to do real wonky things as you get deeper.
Yeah. And
one of those things, which was still kind of theorized, was metallic liquid hydrogen, which is this really crazy form of hydrogen that if I'm not mistaken, we can't quite emulate here in labs. So we have to study it indirectly on Jupiter. So where is that in terms of theory and confirmation and coolness?
Yeah, so I believe that I think the interpretation is still unsettled, but based on what we've seen so far, it is not ruled out. In fact, I would say it's pseudo-confirmed that it's there. There's clearly a electrically conducting moving layer deep down in the planet. And so I don't think there's anything that's ruling out the liquid metallic hydrogen, like you say. And it's basically just the idea that there's so much pressure that it causes the electrons to be free to move because everything gets squashed together so much. And the electrons are then freely moving like they do in a metal. And so, yeah, there's definitely nothing that's ruling that out. What is in fact provisionally ruled out is this rocky core in the center, and so that's the part that's the most confusing right now.
That's fascinating. So if it's not like a solid rocky core, then it still must be something immensely dense, though, right? Because again, it's under all of that. Yeah, so I think it is still rocky, but maybe it's some sort of mix of the metallic hydrogen. I mean, I'm just making this up literally as I'm speaking, so hopefully my science colleagues aren't listening. Because again, this is not actually my area of actual expertise. My expertise is more in the upper atmospheres, the magnetospheres, the plasmas. But yeah, that's what always confused me as well. I mean, well, if it's not a rocky core, but yet there is still this dense material there, then it's got to be some sort of mixture of the metallic hydrogen layer and the rocky material. So,
and what did Jupiter accrete around?
Exactly.
If it's not a rocky core, what was that dense planetesimal chunky
so I think
thing?
that's also part of the story that's coming out is, well, maybe it did accrete around that. And then subsequent to that, there's been planetary evolution. I think that's what a lot of the actual experts in this area are trying to start speculating on, is how that accretion occurred, and then what happened subsequent to that accretion. Right. And of course, the reason this is not just intrinsically interesting for Jupiter is this has really big implications for all the planets that we're finding throughout the universe, throughout the galaxy, all these exoplanets, right? Because there's so many different types of categories of planets now that maybe we can start to get a handle on how planets formed in the first place.
And that's another kind of realm of planetary science, and just like the history of our solar system in general, it's just like, how did we evolve? Like, how did it? I mean, I know we have some very beautiful, like, elegant ideas, but ultimately, again, it's one of those, I don't know, like, and then you have, like, Jupiter throwing us curveballs, like, all right, well, you're not exactly who we thought you were, so what does that mean for the rest of us, you know? I always, so, and tell me if this is accurate, because when I work with, when I used to work with fifth graders who, in California, their science standards happen to be astronomy in fifth grade, I used to describe Jupiter as, like, our big brother in terms of, like, because its magnetosphere was so powerful, it deflected radiation that would otherwise basically pummel Earth. Is that accurate?
So in part, I would say, I don't think that the radiation is significantly affected by the Jovian magnetosphere, but what is definitely affected is the Jovian gravity field.
Yes.
So it definitely causes a lot less asteroids, comets, or whatever, being able to reach the inner solar system. And so that does mean that it is, in fact, well, all right, so let me backtrack. That has definitely been the consensus theory for quite some time, is that the gravity field of Jupiter, it protects us. Again, probably not so much the magnetic field. But I think there's actually debate now about whether that's a net positive or benefit. But the consensus, the standard textbook consensus, is that it did protect us. So you weren't off on the textbook description when you were talking to the fifth graders.
Yeah,
I did have one question. One last question, I think. The asymmetry of the magnetic field of Jupiter, and that there are like really intense pockets at the equator. Have there been any aurorae discovered or observed other than the poles?
That is a great question. I don't think so. I don't think we've really seen concentrations of aurorae there, and you would think that there would be channeled high energetic particles, just like you do at the poles along the principal magnetic field. So, again, I'm literally making this up on the spot, so your viewers are watching BS science happening happening right in front of them. But I mean, maybe it's that the fields, the complications of the fields, the trajectories is the word I'm trying to get out, are so complicated because the predominant magnetic field is still north to south. Here, wait a minute to bring my here. Anyway, but then that predominant magnetic field could have buried within it this comparatively smaller but nonetheless super intense localized magnetic field. And maybe that prevents the particles from being able to precipitate down. But that's a great question.
Radical.
Hey.
All right. Well, I think our team's trying to wrap you up here. So thank you so much for hanging out with us. It was an absolute pleasure talking to you. We hope you had fun as well. And
I did.
Ben, was there any last minute things you wanted to say? Or? We're good.
No, we're good.
We'll have a fun time playing Ultimate Frisbee with your family. The best of luck on your future D&D endeavors. And we are excited to see what comes out of Maven. So thank you. Have a great rest of your weekend.
Thank you. Likewise. Yeah. I'd be happy to come back anytime if you guys want to talk some more Maven energy.
Sounds good.
Cool. Any updates, we get you first.
Yes.
Okay. Sounds good.
All right. Thank you.
Thank you. Bye-bye.